For example 6, when we have to algebraically determine the limit as x approaches infinity of 2x squared minus 3x minus 14 over 3x squared plus 7x plus 2, then once again, we're going to divide all of the numerator and all of the denominator by the highest power of the variable, x squared. So this is going to give us the limit as x approaches infinity of 2x squared over x squared minus 3x over x squared minus 14 over x squared divided by 3x squared over x squared plus 7x over x squared plus 2. When we simplify this, it's going to be the limit as x approaches infinity of 2 plus 3 over x, minus 3 over x minus 14 over x squared, and that's divided by 3 plus 7 over x plus 2 over x squared. And as we've already seen from our previous patterns, all of these are going to tend towards 0, which means that this is just going to leave us with 2 over 3 is our limit. For example 7, some people get scared by this because it doesn't look like it's similar to our previous examples. In this case, when it's asking the limit as x approaches infinity of the cube root of 3x plus 5 over 6x minus 8, then that radical often throws people off. But we know, based on the properties of limits, which we've already done, that this is the same as if I took the cube root of the limit as x approaches infinity of 3x plus 5 over 6x minus 8, and then I just treat the radicand in here like we did the previous examples. So what am I going to do? Inside the radicand, I'm going to divide the numerator and the denominator by x. What's going to happen with that is I'm going to have the cube root of the limit as x approaches infinity of 3x over x plus 5 over x divided by 6x over x minus 8 over x, which is going to simplify to the cube root of the limit as x approaches infinity of 3 plus 5 over x divided by 6 minus 8 over x. And we know that 5 over x and 8 over x are going to tend towards 0 as x is approaching infinity. All that's going to leave us with is the cube root of 3 over 6, and we can obviously reduce that fraction to the cube root of 1 over 2. And there's my limit. If we take a look where the above examples converge towards a certain number, that means that they actually have a limit because it's going towards a specific number. As we already know, right from the first example from today, the sequences can diverge or move away from each other and not approach a value, or they can oscillate between values. And in both these cases, we'd say that no limit exists. So if I take a look at the first example, the limit as n approaches infinity of -2 to the power of n. The first term would be -2 to the power of 1, which is -2. The second term would be -2 to the power of 2, which is 4. Third term would be -2 to the power of 3, which would be -8. As we can see, this is oscillating divergent. It's not approaching a specific number, which means that the limit does not exist. In the second example, the first term is -2 to the power of 1, which is just, -1 to the power of 1, which is just -1. If I have -1 squared, it becomes +1. If I have -1 to the power of 3, it becomes -1 again, and so on and so forth. We just keep jumping in back and forth between -1 and +1, where this is just oscillating between numbers, which means that the limit does not exist. And when I get to the last example, if I have the limit as n approaches infinity of 3 to the power of n minus 1, then I would have 3 to the power of 1 minus 1, which is 1, 3 to the power of 2 minus 1, which is 3, 3 to the power of 3 minus 1, which is 9. And this is just divergent, which means that once again, the limit does not exist. All right, I want you to go and try using the same principle a couple of these examples.